Okay. All right. Okay. So the last topic here we need to just go talk about is something called diagonalization and Cayley-Hamilton theorem. So let me just do a quick recap of where we are at. So recap. Okay, so this is a chapter on eigenvalues and eigenvectors. Right? And the recap is if you're given an n by n matrix, so we know in order to find eigenvalues and eigenvectors, the matrix must be square. Uh, to get the eigenvalues, we first need to form or okay, let's go with form the characteristic polynomial. Yeah, and that's what we call P. A for the matrix A given an n by n matrix A of lambda. And then we solve for the roots of when PA of lambda equals 0. And that gives us the eigenvalues. Okay. And from there, to get the eigenvectors now, what you have to do is that gives the eigenvalues. Then you sub, so maybe I should say what the characteristic polynomial is. So it's equal to the determinant of the matrix A minus lambda along the diagonals. Then you sub, maybe I should say for each distinct, for each different eigenvalue or distinct eigenvalue, let's say lambda I, solve for the null space of this matrix A minus lambda. Okay, let me not use I because I is for the identity, maybe K. K, I. Okay, we spoke about last time why we solve for this null space. That's where all the eigenvectors live, right? So this is called the eigenspace for lambda I. It's where all the eigenvectors for lambda k lives. Okay, so all the eigenvectors for that specific eigenvalue, they live in the space, the null space of A minus ik, right? And this is just a fancy way of saying you're going to solve this system of equations, A minus lambda k, which you will know I. So you work out what that matrix is. You put it equal to some column vector with unknowns, and you solve that equal to 0. Okay, so this here will be a column of n vectors, n unknowns, right? And this here will be n zeros. Okay, so that's a null space. Null space means you're solving a system of linear equations where the right-hand side is 0. All right, so that's where we're at. And in fact, that's all the calculations we're going to do on this topic. And we're not going to go further into more calculations on this. But what we're going to talk about today are some a bit of the theory behind it. We're not going to get too much into the details of this theory, because this stuff could go very deep, and you could spend a lot of time, a few weeks, just studying this one topic. Um, so the first thing is we want to talk about is what is the spectrum of a matrix? Okay, the spectrum of a matrix. The spectrum of a matrix is a very fancy way of saying it's just the list of the eigenvalues. Okay, so let A be some matrix. So Fn by n means some matrix. So for us, we could either be in the reals or the complex. Right? That just means the entries of your matrix come from this field. Then the spectrum of A, we denoted by sigma A, is simply the collection of eigenvalues of A. And this is the important part. They are not necessarily distinct. So we'll see examples later on, but what this part that I've highlighted means is we know when we find the eigenvalues, that is how do we find it? We find it by solving for the roots of a polynomial. And you all know that polynomials, you could have all distinct roots, you could have repeated roots, or you could have complex roots. So when you get repeated roots, this is saying when you're listing the spectrum, you need to list all those roots, how many times it's repeated. So even though, let's say you have a root 10, let's say you get 1, 7, 10, 10, 10, right? This is how you will list the spectrum. So even though this eigenvalue occurs 3 times, you need to list it 3 times. Okay, that's all that means. Now, how many times each eigenvalue appears in the spectrum is given another fancy name. It's called the algebraic multiplicity. Okay, so the algebraic multiplicity of, so now that we know what the spectrum is, we can write something like this. Lambda belongs to sigma of A simply means lambda is an eigenvalue, right? Because sigma A is the spectrum. If you belong to the spectrum, you are an eigenvalue. Okay. So the algebraic multiplicity is just the number of times it appears in the spectrum. So in this case, the algebraic multiplicity of 1 is 1, it appears once. The algebraic multiplicity of 7 is 1. The algebraic multiplicity of 10 is 3. Okay, very easy. It just tells you how many times it appears. The kind of tricky one is this one, the geometric multiplicity. So the geometric multiplicity of an eigenvalue is the dimension of the eigenspace of lambda. So we know that the eigenspace is the null space of some matrix. The dimension of that space, so whether it's 1, 2, 3, and so on, is the geometric multiplicity. Okay, we'll see some examples. So in this example, we're given this matrix A, which is 0, 2, minus 2, 0, and we are told it belongs to C 2 by 2. Why do we put C here? Because this is saying if you get complex eigenvalues, then you can take them. If here was just the real numbers, then you cannot take any complex eigenvalues. Okay, so you want to find the spectrum of A, so that is find the eigenvalues and the algebraic and geometric multiplicity of each of them. Okay, so to get the eigenvalues is, as usual, get the determinant of A minus lambda I So this is the matrix A. You subtract lambda along the diagonals. You know how to get the determinant of a 2 by 2 matrix. It's this one minus this one. Okay. And you set that equal to 0. So you get lambda 1 equal 2i, lambda 2 minus 2i. Okay, so complex roots. So therefore the spectrum is just minus 2i, comma 2i. You just list them. Okay, and since each eigenvalue appears only once, lambda 1 and lambda 2 each have algebraic multiplicity of 1. Okay, and to get the geometric multiplicity, well, we need to solve for the eigenspace. So let's take this one. So we solve A minus lambda I. Okay, that gives this matrix. So if you want to, you could do, for example, A minus 2i by a vector x equals 0. So you could do minus 2i. If you don't want to do row reduction, that's what I mean. If you don't want to do row reduction, you could do something like this. Then write it as a system of equations, and then solve those equations for x1 equals something in terms of x2. Okay? Or you could do row reduction. So in this case, since we're just after the geometric multiplicity, which is the dimension of the eigenspace, so I want to know what is the dimension of this space. So what is the dimension of the null space? A minus 2ii. Right? What is the dimension of this space? Remember what the dimension of a null space is called? It's called the nullity. Right? It's called a nullity. And for matrices, I'll put it here. For matrices, for an n by n matrix, the rank nullity theorem, same rank nullity theorem from linear transformation, because matrices are linear transformations. The rank nullity theorem gives, it's the dimension of the domain. In this case, it's an n by n matrix, so it's just going to be n, right? It's just an n by n matrix, so it will just be n. N equals to the rank of the matrix. And we know to get the rank of a matrix, it's just the number of non-zero rows in row echelon form. So rank plus nullity. Okay, maybe let me not put the matrix A there. Let me do M, right? Because for this question, we're not calculating the rank of A. We were calculating the rank of A minus lambda I. This is the matrix M. Yeah. So we know what N is. So 4 M equals A minus lambda I. We get N equal the rank of A minus lambda I. So you will take the matrix A minus lambda I, put it in row echelon form, and count how many non-zero rows. That's that number. Plus the nullity, which is, this is what we want to find. Nullity of A minus lambda I. Okay, so you could solve for this. You could solve for that one. Okay. That will be the geometric multiplicity. Okay, so that's all they're doing here. This is A minus lambda I in row echelon form. So what is the rank? The rank is the number of non-zero rows. There's only one, so the rank is 1. Therefore, by the rank nullity theorem, the nullity of this matrix is 2 minus 1. Right? It's a 2 by 2. So 2 minus 1 equals 1. So the geometric multiplicity is 1. Okay. And you can repeat again the calculation for the second eigenvalue, which is 2i. You'll get the same thing. Right? So the second eigenvalue here, you just repeat it, you get the same thing. Okay. And there's another example. This one is a equal 1, 0, minus 1, 1. So you can see the course notes for how to go through this example. The calculation is exactly the same. Okay, so that is given a matrix A. How do you get the algebraic multiplicity and the geometric multiplicity? You essentially just need to find the eigenvalues, which is what we already know to do. Okay, so adding to that, so now we're getting into, well, once we get the eigenvalues and the eigenvectors, what could we do with that? So what is one of the use of these eigenvalues and eigenvectors? And for that, we need to recall what a similar matrix is. So we saw previously that two matrices, A and B, are said to be similar if they exist an invertible matrix P such that P inverse AP equals B. Okay, so the matrix A is similar to the matrix B if you could find this any matrix P that is invertible such that P inverse AP, when you work out that left-hand side, you get it equal to B. Okay. So it turns out if two matrices are similar, they have the same set of eigenvalues. They have the same spectrum. That's this theorem. Let A and B be similar matrices over F n cross n. Then the spectrum of A equals the spectrum of B. In other words, they have the same eigenvalues. Right? Yeah, the same eigenvalues. Okay, so let's go through the proof. The proof is a very nice proof and it's very easy. We just actually the proof here, we're not calculating anything. We're not even we're not calculating any eigenvalues and eigenvectors, something. We're just using properties of matrices. Okay, so let's go through this proof. So suppose A and B are similar matrices by definition, right? So now you need to recall, what does that mean? There exists, that's what that is, there exists an invertible matrix P such that P inverse AP equals B. Okay, so far, just apply the definition. Now I need to show that the spectrum of A equals the spectrum of B. So the spectrum, where do you get the spectrum from? The spectrum is a list of eigenvalues. Where do you get that from? The eigenvalues comes from the characteristic polynomial. So all you really have to do, or another way of saying this, is that the characteristic polynomial of the matrix A is the same as the characteristic polynomial of the matrix B. So these two matrices, they could be different and they give the same characteristic polynomial. Okay, so they will have the same spectrum, the same eigenvalues. And how to do that? Well, just take one of them. Let's take this one and try to show it is equal to the characteristic polynomial of A. Okay, so start with the characteristic polynomial of B. By definition, that is equal to the determinant of the matrix minus lambda times I. Okay, so that's the definition of what the characteristic polynomial is. And now we're just going to use the fact. Maybe let me write this out for you guys. Okay, so we go through the proof one. What term was that? 723. Proof of theorem 7.2.3. Okay, we'll go through it. So I'll show you the calculation is very easy. So suppose matrix A and B are similar. Then what does it mean to be similar? There exists an invertible matrix, call him P, such that P inverse B times P equals A. Okay, or if you want to, I think we could do P inverse AP. Does it go that side? I don't want to write something different and confuse you all. Yeah. So this is true. This is true, by the way. If so we didn't do it, but similar matrices is an equivalence relation. So it's reflexive, symmetric, and transitive. So you could do P inverse AP equal A, or let me write it like what they do. Or you could do P inverse A P equals B. Right? Same thing. The matrix P will just be different. It'll be something. Okay, so such that P inverse AP equals B. Required to show, what do I want to show? I want to show that the spectrum of A is the same as the spectrum of B. Another way of saying this is that the characteristic polynomial of A is equal to the characteristic polynomial of B. Okay, so let me take the characteristic polynomial of B and show it's equal to A. So consider the characteristic polynomial of B. Okay, by definition, that is equal to the determinant of the matrix minus lambda I. Okay, now I'm going to sub in what is B. Look, B is P inverse AP. So sub that in. So this is the determinant of P inverse AP minus lambda I. Okay, so now what I'm going to do for this I is the identity matrix, right? I is the identity matrix. So I'm going to do something a bit clever here. And I'm going to replace I by P inverse IP. Right? Do you see that? What I do? What did I do there? Let me write it. So we know that the identity matrix, if you work out what is P inverse times I, that's P inverse. And P inverse times P is still I. So I'm just replacing that over here. Okay? And the reason why I'm doing that is because you see over here it's A, and to the left is P inverse, and to the right is P. So I want the same sort of form. I want the same sort of form to be over here. Okay? And now what I could do is, this is the determinant of, so now I'm going to pull out P inverse to the left and P to the right. So P inverse, let me use a different bracket. Do this bracket. P inverse, and then I'll do A minus lambda I. Okay, so I pull out, let's do P inverse. So I pull out P inverse to the left and I pull out P to the right. Now remember, these are matrices, so you can't go flipping them around, right? For example, you can't just interchange these two matrices, okay? Because matrix multiplication is not commutative. So you need to keep P inverse on the left, P on the right, okay? But remember, we have a result for determinants, and that is, so now I'm going to apply this result that we use. So remember that the determinant of, don't use A and B, maybe M and N is equal to the determinant of M by the determinant of M, N, right? So essentially I could break this up, okay? So I'm splitting this apart into three determinants. So what I wrote here is for two determinants, but it holds also for three. So N, right? So even that's for two matrices, but it holds for any finite number. So I'm just going to break this up into the determinant of P inverse multiplied by the determinant of A minus lambda I multiplied by the determinant of P, right? So I just split everything apart into three things. Now the determinant of a matrix, is that a matrix? No, the determinant of a matrix is a number, right? This is just a number, this is a number, this is a number. And numbers commute, right? And numbers commute. So these are numbers, so I could flip them around. Okay, so these are numbers, so I can move them around. So I'm going to rewrite that as the determinant of, let's do P inverse. And this guy over here is a number, so I'm just going to move it over here. The determinant of P by the determinant of A minus lambda I. And for these two, I'm just going to recombine it again. Okay, so I'm using the same result we used to split it apart to put it back together. This is the determinant of P inverse P by the determinant of A minus lambda I. The determinant of P inverse AP, P inverse P is just I by the determinant of A minus lambda I, and the determinant of the identity matrix is 1, right? This guy is always equal to 1. So this gives simply, I'll write it here, this is 1 times the determinant of A minus lambda I. And what is the determinant of A minus lambda I? That is just the characteristic polynomial of A. Okay, that's the characteristic polynomial of A. So what did we prove? We proved that the characteristic polynomial of P is equal to the characteristic polynomial of A. Okay, therefore we're done. Right? So very straightforward proof. I didn't calculate any eigenvalues, any eigenvectors. All we did was just use simple matrix results, right? That the determinant could be broken up into this way, and that you could rewrite. So I suppose the only trick you need to remember is to rewrite the identity like this. Okay, and then pull P inverse out to the left, P out to the right, split everything apart. Since these are numbers, you can move this number over here, then recombine these two. You get the determinant of the identity, which is 1, and you get P of A. Okay. So once you sit and write this proof out down 1 time, 2 time, it should be clear. Right? Okay. So the same proof here. So two similar matrices have the same spectrum, same list of eigenvalues. Then there's a very useful result that sort of helps us when we want to determine the geometric multiplicity if we have the algebraic multiplicity, right? And that's given by this result. It's saying if we have a matrix, an n by n matrix, and suppose that alpha is the algebraic multiplicity and beta is the geometric multiplicity of a specific eigenvalue, then the algebraic multiplicity is always bigger than or equal to the geometric multiplicity. Okay, let me show you. Let me give you an example of that. Right? So what that one is saying is that the algebraic, okay, let's say it this way. It's just the geometric, is that the geometric multiplicity of an eigen value is always less than or equal to the algebraic multiplicity. Okay, and now you need to ask yourself the question, what is the smallest the geometric multiplicity could be? What is the geometric multiplicity? It's the dimension of the null space of A minus lambda I, right? In other words, it's the dimension of a subspace. So when we are talking about dimensions of vector spaces, did we ever have a negative dimension? No. Dimensions were non-negative. They were non-negative whole numbers. So 0, 1, 2, 3, and so on. These are dimensions. Could we ever have the dimension of where the eigenvectors live? Could that ever be 0? So the dimension, the vector space with dimension equal to 0. There's only one vector space with dimension 0. It's the 0 vector space, the 0 subspace. Okay, so the subspace with just the 0 vector, that is the only one that has dimension 0. So my question to you all is, could this ever be the eigenspace of a matrix? Anyone want to take a guess? The eigenspace is where the eigenvectors live. I forgot how to make polls in this, polls. One second, huh? Mhm. Okay, so you should get that question. So take 10 seconds to decide. And I think it should tell you what the answer is as well. Okay, so who's put in yes? Think about it. Could if the geometric multiplicity is zero, right? If the geometric multiplicity is zero, that means the space where those eigenvectors live is this space, the zero subspace. Okay, and remember the condition of an eigenvector. An eigenvector is a non-zero vector. Okay, so now the nodes start spiking. Yeah. Okay. So the answer is no, the geometric multiplicity cannot be zero because the eigenvectors cannot be zero. In other words, the geometric multiplicity, here's one, must be bigger than or equal to one. Okay. So let me give you this example. Say we have some matrix with spectrum, a half, 12, 100, 1/2, 7, 12, a half, and -2. Okay. So this matrix will be a 1, 2, 3, 4, 5, 6, 7, 8. Right? So this is an 8 by 8 matrix. Then what is the algebraic multiplicity? What is the algebraic multiplicity of each of these? So the algebraic multiplicity of lambda1 equals a half is how many times did a half show up? 1 time, 2 times, 3 times. 3 times. The algebraic multiplicity, maybe let me do it in like a table. That might be easier. Yeah, eigenvalues, algebraic multiplicity, geometric. So we have the eigenvalue, the algebraic multiplicity, geometric multiplicity. So half, 7, what should I put there? 12, 100, -2. Okay, the algebraic multiplicity of a half, how many times did a half appear? It appeared 3 times. How many times did 7 appear? It appeared 1 time. How many times did 12 appear? 2 times. 100 appeared 1 time, and -2 appeared 1 time. Okay, and the geometric multiplicity, so we have a bound for that. We know that the geometric multiplicity is between 1 and the algebraic multiplicity. So the geometric multiplicity for a half, now we will have to calculate it. It could be either 1, 2, or 3. We need to work it out. Okay, so depending on the matrix, you would then need to get the rank of the matrix, right? You'll have to get the rank of A minus 1/2 I, and then use rank nullity to get the nullity. For the eigenvalue 7, the algebraic multiplicity is 1. So the geometric multiplicity, what could that be? The geometric multiplicity is between 1 and the algebraic 1. So if the algebraic multiplicity is 1, the only possibility the geometric multiplicity can be is 1. Right? Because it's between this one and this one. So it could only be 1. In other words, when we were finding the eigenvalues, when we got an eigenvalue only one time we are guaranteed that the geometric multiplicity, we are guaranteed that the space where those eigenvalues, those eigenvectors live is a one-dimensional space. Okay, so 12, the algebraic multiplicity is 2, so the geometric one could be either 1 or 2. We need to calculate this. Okay, you'll have to work out what that one is. 100 is 1, so anytime you see the algebraic multiplicity as 1, the geometric multiplicity is also 1. Okay. So it's a very useful result. Okay. Okay, so the proof of it, no need to know the proof, but that is what this result is saying. Now, we know what similar matrices mean, and we know that if two matrices are similar, we just worked out they have the same eigenvalues. This is telling us something very useful we could do with that, and that is if a matrix A is diagonalizable, so what does that mean? We say a matrix is diagonalizable if A is similar to a diagonal matrix. So that means there exists in an invertible matrix. Over here is where we will put P. Okay, let me just scroll back up to this thing. Right? So we're looking at this. Two matrices are similar if there exists an invertible matrix P. We say a matrix is diagonalizable if instead of this matrix P, you have a diagonal matrix. So it's a special case where the matrix P is a diagonal matrix. That's all this definition is saying. Okay. If A is similar to a diagonal matrix, that means there exists a diagonal matrix D and an invertible matrix P such that P inverse AP equals D. Oh, sorry, what did I put here? I said P was the diagonal one. Yeah, sorry about that. It was B. B is the diagonal one, right? So if B is the diagonal matrix, right, then it's diagonal. And so how could we tell when a matrix is diagonalizable? So that's given by this result. And it says, if you have some matrix A, that's an n by n matrix, then P is an invertible matrix such that P inverse AP equals D, where D is a diagonal matrix. So this notation here means that it's a diagonal matrix and the entries are these things, D1, D2, Dn, and up here is 0 and down here is 0, right? That's what this thing is. Okay. If and only if for I between 1 and n, the ith column of P is an eigenvector of A corresponding to Di. Okay, don't worry about this. I will show you in an example what this is saying. This is giving us a recipe for how to find or construct this matrix P. The second one is saying it's telling us when a matrix is diagonalizable. It's saying a matrix A is diagonalizable if and only if it has n linearly independent eigenvectors. In other words, so we could use this result to prove this guy. And this one is saying that a matrix A is diagonalizable if and only if it has n different eigenvalues. So if it happens when you solve for the eigenvalues of A, all of them are different, no repeats. They could be complex, that's fine, but no repeats, then your matrix is diagonalizable. And if it is diagonalizable, then we could write P inverse A P equal to D. So what we're going to talk about is how to get this matrix D and how to get this matrix P. We know A. Okay. Yeah, so this one is what I just said there. If you solve for the eigenvalues and they are all different, then it's diagonalizable. Okay, so I have to show you how to get that. So we have the examples here. Okay. But I'll just go through it with you. Right? So I'll just give you an example. So let's just make up a case. So say A is a let's say is a 3x3 make so let me write it like this. Say A is a 3x3 matrix with spectrum. So now we know what this means. This is a fancy way of saying the eigenvalues equal to -1, 7, 1/5. Okay, they're all different. Since there are 3 distinct eigenvalues. So since I'm saying since they are all different, A is diagonalizable. Okay. Once all the eigenvalues are different, it's diagonalizable. If any one of these guys was repeated, no, you can't diagonalize it. Okay. Let's just say as well that the eigenvalue -1 had an eigenvector, right? So let's just say one possible eigenvector for it is, I don't know, 1, 0, 7, let's just say. And lambda 2, so I'm just making this up by the way. I'm not working anything out in my head. I'm just making this up, right? Because we already know how to get the eigenvalues and the eigenvector. I'm just showing you how to construct that matrix P and the matrix D. So let's just say the eigenvalue 7 had the eigenvector 0, -2, -5, right? And let's just say the eigenvalue 1/5 had the eigenvector 0, no, that one will be 0. 0, let's do, yeah, this one will be 0, this one will be 0, 9, right? Right, so let's just say when you work it out for each eigenvalue, you find a corresponding eigenvector. Now the eigenvectors are not, there's no one eigenvector. Remember, if this is the eigenvector, any multiple of it is an eigenvector. If this is an eigenvector, any multiple of it is 1. If this is an eigenvector, any multiple of it is 1. Right, so there are many different eigenvectors you could write down. Let's just say these are true. Then there exists a matrix P such that P inverse AP equals D. So I'm going to tell you how to get this matrix P. This matrix P is equal to, see if you could figure out what I'm doing here. 1, 0, 7. So P is a 3 by 3 matrix. The second column is 0, -2, 5. The third column is 0, 9, 0. Did you see what I did there? If this guy, let's call him V1, let's call him V2, let's call him V3, then all you have to do to construct this matrix P is put the eigen vectors as the columns. Right? So you just stack the eigenvectors as the columns. That's what that theorem was telling us. And the corresponding diagonal matrix will be, so since in the first column, I put the eigenvector corresponding to -1, in the first entry, it will be a -1. Since the second column, I put the eigenvector corresponding to 7, this guy here will be 7, and the last one will be 1/5. So the diagonal entries of this matrix D is precisely the eigenvalues. Okay, so this is lambda1, lambda2, lambda3. Do you have to put it in this order? No, if you wanted to, you could have put V2 over here and V1 over here. But in that case, these two eigenvalues will have to be swapped. Okay, so the eigenvalues appear in the position that you put the eigenvector. Okay, so very easy. Right, so you could go through these examples. They're doing exactly the same thing. And I even color coded for you. So blue, green, red, blue, green, red. So you know where it's going. Okay, so the last topic is something called Cayley-Hamilton theorem. Okay. Now, Cayley-Hamilton theorem, we're not going to do the proof of it. It's a big theorem in linear algebra. A lot of other results come from it or uses it. It's a very interesting result, right? And it basically says that if A is an n by n matrix, then, so in order for Cayley-Hamilton theorem to work, by the way, the matrix has to allow for complex numbers, okay? So just note that. In order for this theorem to work, you need to be in this space, not R, not R, okay? So then A satisfies its characteristic equation, right? What does that mean? The characteristic equation of A, that is PA of lambda. That is the determinant. How do we get that? That is the determinant of A minus lambda I equal 0. Okay, so when you work this out, you get a polynomial. Okay, it's saying if you plug A into that polynomial, it will work. A satisfies its characteristic equation or characteristic polynomial. Okay, we'll do an example so you see what we mean. Right, so the best way to show you this is by use of an example. So 2 more examples. So suppose the matrix A is -1, 1, -1, 2, 2. This is one of the use of it. So I said there are many uses. The use that you need to know is this: how to use Cayley-Hamilton theorem to get the inverse of a matrix. Okay, that's what we need. How to get the inverse of a matrix using Cayley-Hamilton theorem. Very easy. So the first thing they are checking is that the matrix A is invertible. So they just calculating the determinant. So no need to do that. If I give you this in an exam, you can trust me. If I tell you find the inverse of A, you can trust me that A does have an inverse, right? So no need to check if it's invertible. What you need to do is get the characteristic polynomial of A. So you need to work out what is this. So it's the matrix A, but you subtract lambda along the diagonal. Okay, and the determinant, you know, is this one by this one minus this one by this one. So simplify and you get lambda squared minus 3 lambda equal 4. This is the characteristic polynomial. Cayley-Hamilton theorem tells us if you replace lambda by the matrix itself, if you replace lambda by the matrix A, then this thing equals 0. It will not be the number 0, the 0 matrix. Because if you replace lambda by A, you get a matrix equation. So everything there is a matrix. So let's do that. Right? So I'm going to replace lambda by A. So use Cayley-Hamilton theorem. I know it's over here, but I'm just going to show you how I write it. So it's lambda squared, so that becomes A squared. Minus 3 lambda, that becomes minus 3 times A. Plus 4. Now, are you just going to put plus 4? This is now a matrix equation. Every entry must be a matrix. So you can't just add the number 4 to a matrix just like that. We need to adjust something. We need to do 4 multiplied by I. We need to convert the 4 into a matrix. So just remember that. A lot of people forget this. When you have just a number by itself, you need to slap on an I to the end to convert it into a matrix. Okay, so this is now a matrix equation, and it is equal to the 0 matrix. Right, this is a matrix. So it is equal to the 0 matrix. Okay, so that's what they have here. A squared minus 3a plus 4i equals 0. So this is the 0 matrix, not the number 0, 0 matrix. And you do 4 times I because you cannot add a number to a matrix. So they want the inverse of A. So inverse means I need to get the inverse into this equation. So multiply both sides by A inverse on the left, right? So multiply on the left by A inverse. Of course, A inverse by the 0 matrix is 0. So A inverse by A is A. So now use distributive law. A inverse by A is the identity. A inverse by the identity is A inverse. Okay, so you get this equation. What do they want? They want the inverse. So solve this for A inverse. Dump everything else over to the right-hand side. When you do that, you get A inverse equals 1/4 into 3 times the identity minus A. This is an equation for the inverse. So all you have to do now is plug in what A is. Look, you're given A here. Plug him in over here. Work out the matrix multiplication and addition. You all know how to do that. And you get the inverse. Right? So it's a way to get the equation of the inverse with respect to the matrix. Right? So very cool way to go to do things. Okay, here's a 3x3 example. Same story. In this one, you'll have a cubic polynomial. You all remember how to factorize cubic polynomials? Okay, don't worry. I'm not gonna give you a cubic to factorize in an exam, right? So up to quadratic, no cubic, right? So you'll go through this example, same story. Okay. So this one is a bit more working because you have to do a 3x3 matrix, but it's the same step. A very useful thing or useful result you could use this for is everyone knows from high school that the inverse of a 2x2 matrix A, B, C, D is given by this, right? It's 1 over the determinant by D minus B minus C minus A, right? Everyone knows it. We could use Cayley-Hamilton theorem to prove this, to prove this result, okay? So the steps are exactly the same. Look, the proof is finished here, right? So just 6 lines. So the first thing, we need to find the characteristic polynomial of A. So work out what is the determinant of A minus lambda I. That is the matrix A, and you subtract lambda along the diagonals. Then you get the determinant. So it's this one by this one minus this one by this one. So when you work that out and you simplify, you get this result. Okay, this is the characteristic polynomial. Cayley-Hamilton theorem tells us if you replace lambda in this equation by the matrix A, that is a matrix equation equal to 0. This is what Cayley-Hamilton theorem tells us. If you take the matrix A and you sub it in here for lambda, in other words, P of A equal 0. This again is the 0 matrix, right? I need to keep stressing this. That's the 0 matrix. Cayley-Hamilton theorem is a matrix equation. Everything is a matrix, right? So let's rewrite this as a matrix equation. So anywhere you see lambda, put in A. So A squared minus A plus D, A plus AD minus BC. And do you leave that as a number? AD minus BC is a number. No, you need to convert it to a matrix. So put I equal 0 matrix. Right, that's what we have here. Now, what do I want to prove? I want to prove the inverse is equal to this. So I need the inverse to appear here. So multiply both sides. So Cayley-Hamilton tells us how to set up this equation. Now, once you set up this equation, you need to get the inverse in there. How do you get the inverse in there? Multiply both sides by the inverse, right? So multiply both sides by the inverse. And you get, so A inverse times this. So A inverse by A squared is A. A inverse by A is identity, right? Don't put minus A plus D there. You'll lose a mark. It's minus A plus D, I. It's a matrix. Then A inverse by I is A inverse. AD minus BC, A inverse equals 0. So solve for A inverse. Dump everything else over on the right-hand side. Okay, so solve for A inverse. Right, we could do that. Let's go through that. So let's solve this for A inverse. So I get AD minus BC, A inverse. So I'm dumping everything over. So it becomes A plus D, I minus A. Right? So take these two guys over to this side. And this gives AD minus BC, A inverse. So A plus DI. You all know what that matrix looks like? I is the identity. I is the 1, 1, 0, 0. So A plus DI is A plus D, A plus D, 0, 0. Minus, what is the matrix A? A is A, B, C, D. Work out that. So you all know how to subtract matrices. A plus D minus A is D, minus B. 0 minus C is minus C. A plus D minus D is A. Right? So take this guy over. So you get A inverse equals, this is a number. Right? That's a number. So it becomes 1 divided by that number. Right? That's the determinant, of course. D minus B minus C, A. Right? Very easy proof. Okay, so that is a use of Cayley Hamilton to get matrix inverse. Okay, so your meme. Okay, so that's it. Finish everything. Okay, any questions?